3.2 talks about polynomial functions and their graphs. They start this backwards, which is really good. They start, if we give you a polynomial in factored form, then guess what? You can sketch a graph easily. The rest of the chapter, almost the rest of it, is trying to factor a polynomial. What a polynomial is, it's a function that looks like this, in which n is a whole number, talking about the power, and the coefficients are real numbers. So n could be 1, 2, 3, 4, all the way up. It can be negative, it can be a fraction or a decimal. If that's the case, then we break all of these problems based on the leading coefficient. The leading coefficient determines how this graph behaves when x is very, very large. That's what n behavior means. X is very, very large or very, very small. When I say very small, I don't mean like 0.001. I mean like a negative trillion. That's small. So as x grows to infinity or x grows to negative infinity, the leading term determines the end behavior of the graph. There are two cases. If this power, since it could be a whole number, is even, that is, n equal 2, 4, 6, 8, ... n is odd, meaning 1, 3, 5, 7, any of those. If n is even, then the end behavior will look like a parabola if the leading coefficient is positive, and if the leading coefficient is negative, then that graph is going to look like an upside down parabola. Now, what's happening between here, that's what the majority of the chapter is about. That's why we need to find intercepts. But we know if you go far left and far right, it's going to look like this or this. Same deal happens with odds. If the leading coefficient is positive, then the graph is going to look like this. Is how I think about it. Even, I think of x squared or negative x squared, if you remember. And odd, do you remember how these look? Or negative that, right? So if it's positive, the end behavior would be like, and I need the end behavior to sketch a graph. And if the leading coefficient is negative, then doesn't that look like a negative cube? So when they say on the next set of problems, describe the end behavior of the graph. Again, what's happening in between, that's the entire chapter. 3.2, you're given that. But 3.3, 3.4, 3.5, 3.6, all of these are working toward how do you combine those into one? Not 3.6, 3.8, 3.7. So, and describe the end behavior. What's the leading term? The leading term is the term with the highest power. It's x cubed. So this graph, on the long run, it's going to look like y equal x cubed. There you go. That's all you have to do. For when x is 1,000 or 1,000,000 or 1,000,000,000, the graph is going to look like a cubic. Again, what's happening in between? We're not there yet. How about this? Well, let's see. X to the fourth, x squared. So this is the leading term. X to the fourth, they all look like a parabola, if that's positive. Here, they're trying to kind of throw you off because there's an x there, and if you distribute that, isn't that x to the fifth? If you distribute that, so we put a squiggly line saying the dominating term is negative 9x to the 11. Do you see that? If I multiply this out, this is 9x to the 5th minus 9x to the 11. So the leading term is negative x to the, well, x to the 11 looks like a cubic, but the fact that this is negative, it's going to flip-flop. And the end behavior look like that. Again, what's happening in between, that is for the next sections to come. Now we're giving you things that are factored. We're giving you polynomials that are factored. So if I go ahead and start by graphing this, intercepts are a key. I know this behaves like x squared. So I know it's gonna look like this somewhat. What's missing? The y-intercept, that's the easiest to find. If you let x equal 0, what does y equal? -1 times -2 is -2, right? And what else? This graph has an intercept at 1 and at -2. It's a parabola. Well, if this is the piece to the right, then I know it must pick up from the intercept. And this must pick up from the intercept. Now comes the most important part. The multiplicity. The multiplicity on those is a 1. So I have x equal 1 multiplicity 1. And I have x equal -2 multiplicity 1. The multiplicity indicates, so that's going to behave at this 0, because that's where this equals 0. That's going to behave like y equal x. Y equal x is a straight line. It's going to go through the intercept. And here, how does it look like? Well, doesn't that look like, again, x to the 1? That's going to look like a straight line. I know that doesn't mean much to you because you're not used to this, but you'll see what I mean once I get. If you notice, I took the same problem and I took on all combinations you can ever think of. If I look at part B, this behaves like x what? X squared times x, that's x cubed. Positive x cubed. Okay, so like this. What are the zeros? If x equals 0, think about it. I'm looking at -1 times 2 squared, that's -4. Okay, now I have x equal 1 and x equal -2. X equal 1 is a 0, and x equal -2 is also a 0. Okay, and the key point is the multiplicity. Do you see the multiplicity here is a 1? That means at x equal 1, this is going to look like a straight line. A straight line. Right? Don't need that. A graph must go through its intercept. And now we go to the other intercept. Now comes the tricky part. Does this graph look like this? Does this graph look like this? Well, hey, no need to guess. Look at the multiplicity. You know it's going to end up being here, right? The multiplicity on this 0 is a 2. When this comes in and it must touch that, it must cross or intersect the intercept. If it's a parabola, how can you make this look like a parabola just around that 0? Well, don't you have to come back down to make it look like a parabola? And now it matches the odd. And there it is. How about the problem after that? What does this behave like? X squared times x, that's x cubed again. I have a good idea of how that looks like. If x equals 0, I'll get -1 squared times 2, which is 2. The graph goes through that point. Alright, I know I have the intercepts at 1, -2. Alright, well, let's start left to right, I suppose. It doesn't really matter. So from the left, since that point's down, it's going to hit that point. Now, what's the multiplicity on that? That's a 1. That means around that 0, it's going to look like a straight line. So we know it's going to look like this, a straight line. It has to go through that. And it must get to the other intercept. Now, do you see that this has a multiplicity too? That means around that 0, this should look like a parabola. Well, how do you make this look like a parabola? It must go back up. That's the only way it would look like a parabola. What if I squared both? Well, what difference does it make? This has a 0 at 1. This has a 0 at -2. All of them are going to be like that. This behaves like x squared times x squared is x to the 4th. If I let x equal 0, I get negative 1 squared, which is 1 times 4, which is 4. Left to right. The left 0. I'm going to come down, and do you see that that has multiplicity 2? If it has multiplicity 2, that means it's going to look like a parabola. The only way it could look like a parabola, if you go up, do you see that that looks like a parabola right there? And it must go through the intercepts, no other way around it. And do you see that x equal 1 is also a parabola? How do I make this look like a parabola? Isn't it by going back up? And that's how the graph looks like. So they want us to say x equal 1 multiplicity 2 and x equal negative 2 multiplicity 2. Why is the multiplicity important? Because I look at the multiplicity, it better look like a parabola. Now, up or down, it doesn't matter. Both of those are parabolas. How about this problem? Well, I know it's going to cross at 1, negative 2, no big secret. We all know that. 1 is right there. I'll get to that in a minute. 3 is right, negative 2 is right there. I'll get to that in a minute. This is dominated by x times x cubed, which is x to the 4th. It looks like this. If x equals 0, negative 1 times 8 is negative 8. Well, here I have to improvise. I'm going to say that's negative 4 and that's negative 8. Alright, and then what? I have x equal 1 multiplicity 1, x equal negative 2 multiplicity 3. Left to right. When you say multiplicity 3, multiplicity 1 looks like a straight line because of y equal x. Multiplicity 2 must look like a parabola this way, and of course this could be this way, and this could be this way. Y equal x cubed. It must look like this or like this. There's no telling which of the cases it is. It's not like, oh, positive or negative, because it depends on what you have. I know the upper left has to be going up. I want to make it, again, since that is cubic, I want to make it look like a cubic, but I already have a piece of it. Doesn't a cubic look like this? So it has to look like a cubic around that 0. It must cross through, okay, the reason it's going really off because I scaled it way off. Otherwise it will be a smooth, nice graph. So let's say that's negative 2, negative 4, negative 6. That's negative 8. So around that 0, it must look like a cubic. That has to show. Go through the intercept. Now what? I touch, do I go back down or do I go, well, it has to look like that. And I know the multiplicity is 1, meaning like a straight line. And I could erase that piece. And there it is. It's satisfying what I need. How about this graph? Well, the same deal. I know it's going to cross at 1. No big secret. All of these are going to cross at 1 because I picked them that way. There's the 1. There's the 3. Now, without the end behavior, I can't sketch a graph because I don't know if this cubic looks like this or looks like this. I need the end behavior to figure that one out. What dominates the top? X cubed times x, x to the 4th. The graph looks like this. So I know already, since this has a multiplicity 3 and this points to the right, I know that the right side graph is going to look like a cubic around that 0. And the left, I know it's going to come straight across like y equal x, because x equal negative 2 has multiplicity 1. Well, let's see. What is the y-intercept? If I put 0 in for x, what do I get? I get a negative 1 times 2, which is negative 2. Oops. Done deal. There it is. How about this graph? Well, again, no big secret. We all know this. My goal is to get you sick of this, which is a good thing in math, by the way. What if I switch those? Well, let's see. This is x squared times x cubed, which is x to the 5th. Odd. It's going to look like this. The fact that this is the fact that x equal 1 multiplicity 2, well, it has to, and behavior are a must. And the only way this could look like a parabola if this goes back up. Are we following? And this, since the left side looks like this, so I know how that goes. It has to go like this because the multiplicity is 3. So what's the y-intercept? Well, it better be up there. If I set x equal to 0, negative 1 squared is 1 times 8 is 8. 2, 4, 6, 8. There you go. And that's how we do all of these graphs. How about this one? What if I cube 2? Pretty much I take on all the combinations until hopefully you really get the hang of this, because this is a must before we move to the next section.